concentration of the solute. So if you had a solution, let's say you had some soda, and you wanted to dilute it, what would you do? Add water. So if you're going to dilute something, you add more solvent. And in almost all the cases for us, that solvent is going to be water. Our solution is going to be based on water. And so when you dilute something, you're just going to add more water. Now if we look at our molarity equation, molarity is moles over liters. If we add water to our solution, which of these things are going to change? Liters is going to change. This is volume. If you add more water, your volume is going to change. Is your volume going to get larger or smaller? If you add water, your volume is going to go up, right? So if this goes up, is the moles of solute going to change? If I have salt water and I add more water, does the moles of salt in there change? No. And so moles stays the same, volume or liters goes up. If that happens, molarity goes down. So when you dilute something, concentration goes down because volume goes up. The same amount of solute is in there, it's now spread out over a larger volume. So the equation that we're going to use for dilutions is M1V1 equals M2V2. Just like before, the 1s are the initial and the 2s are the final. M is molarity and V is volume. So this means the initial molarity times the initial volume equals the final molarity times the final volume. And that's because if we rearrange this, what we get is molarity times liters equals mole. And we said that the moles, the amount of solute in there, never changes. If I have salt water and I add more water, the amount of salt doesn't change. And so the amount of salt in my solution has to be the same before as after. And if mole never changes, what you get is the number of moles before equals moles after. So this is just an explanation of that equation. It's a simple equation. It is not on your cheat sheet. This is another one that's not on the cheat sheet, but it's simple enough. You'll be given 3 of the 4 variables. You'll plug in for the 4th. And it can be any of them that are missing. So if you rearrange them, those are 4 separate equations. My suggestion is just remember the 1 and you can rearrange it. So here is an example. We're going to do several examples looking at different ways that we can use this equation. So the equation is M1V1 equals M2V2. In this specific example, it says we are starting with 175 milliliters of a 1.6 molar solution of lithium chloride, and we're going to dilute it to 1 liter. We need to find the new concentration. So of these 4 variables, which is the one I'm trying to solve for? We're looking for new concentration. M2. M2 is what we're looking for. So what is M1? The initial concentration, 1.6 molar. Volume 1 is 175 milliliters. And then V2 is 1 liter. Like with our gas laws, it doesn't matter what units our volumes are in as long as they are the same unit. So in this case, we have one that's in milliliters, one that's in liters. We'd have to convert one of them to the other one, but it doesn't matter which. Does anybody have a favorite way they like to go? Which one seems easier to use? All milliliters? So how many milliliters are in 1 liter? 1,000. So now we have molarity, milliliters, milliliters. So 1.6 times 175 equals M2 times 1,000 . .28. 0.28 molar. So in this case, we were looking for M2. Here's another one. This is, we need to make 10 liters of a 1.2 molar solution. It's asking if we are going to use 2.5 liters of our initial solution, what concentration would it have to be? So in this situation, looking at our variables, which of the 4 variables is the one we're trying to solve? It's telling us in the end we need to have 10 liters of 1.2 molar. So it's telling us the final. So we have both of the 2's. What we're looking for is M1. So M2 is 1.2. M1 is what we're looking for. V1 is 2.5. V2 is 10 liters. So what we get is M1 times 2.5 equals 1.2 times 10 . No more difficult than the other one. It was just picking the numbers out of the question to figure out what you're solving for. Here's a third one. This says, I'm doing a reaction, and I need 100 milliliters of 3 molar HCl. That is what I need for my reaction. I go onto my shelf, and I find that I have a stock solution. A stock solution is the concentrated form that we keep on the shelf. We have a stock solution that is 10 molar, but I only have 13 milliliters of it. And the question is, can I do my experiment, or do I need to order more and wait till it comes in? There are a couple of ways that we can do this. Anybody look at that and have a strategy jump up? Because we actually have. We have M1, we have M2, we have M2, I don't know what I said. We have M1 and M2 and V1 and V2. We would seem to have all 4 numbers. So it's not just pick which one's missing and solve for it. There's a little bit of thought that has to go into this. So I know that I need 100 milliliters of a 3 molar solution. But what I have is 13 milliliters of a 10 molar solution. What you're going to have to do is you're going to have to pick one of the four and act like you don't have it. Solve for it, and then compare what you solved for to what you actually have. And if you stop and think about it, it will work for any of the four. It's just some of them are a little more conceptually hard to get your head around. To me, the easiest one to drop out is this one. Basically what that's saying is if I ignore that one, I'm asking the question, if I have 13 milliliters of a 10 molar solution and I dilute it to the point that it's 3 molar, what volume of solution can I make? If I make at least 100 milliliters, I have enough. If I make less than 100 milliliters, I don't have enough. All of the other ones, you can do the logic and figure out what does this mean, but it's not as straightforward, at least in my head. So let us leave out V2. If I leave out V2, M1 is the concentrated solution, which is 10 molar. V1, I have 13 milliliters of it. I'm diluting it to 3 molar. And I'm going to solve for V2 this time. So we have 10 times 13 equals 3 times V2. So you get 130. What is it at 43? So this is volume. Like with gas laws, because I put milliliters in, I get milliliters out. So this means with the stock solution that I have on the bench, I can make 43 milliliters of 3 molar solution. Can I do my experiment? No. I need 100 milliliters of it. I can only make 43. If I add more water to get more volume, all of a sudden I no longer have 3 molar. And so in this case, I cannot do my experiment. When we dilute things, we talk about dilutions very easily in lab. Okay? And when we dilute it, we say how much we diluted something by talking about its dilution factor. So this is an example of a dilution. Luckily, it's colored. If we're diluting something like a salt solution or a sugar solution, we can't see that. And so we have to trust that it is diluted. But in this case, when it's concentrated, it's dark red. And then as it gets diluted, it gets lighter and lighter. Because the concentration of whatever is in there that's making it red is getting lower. If you have a lower concentration of your dye, it's going to be less red. So when we talk about dilution factors, we say it is a something-fold dilution. When I say that, what I mean as an example is a two-fold dilution. A two-fold dilution would mean the volume went up by a factor of 2, and so the concentration went down by a factor of 2. If volume goes up by a factor of 2, it doubles. M2, the final concentration, gets cut in half. If the volume doubles, the concentration gets cut in half. If the volume triples, the concentration is going to go down by a factor of 3, which means it will now be a third of where it started. So that would be a 3-fold dilution. You can also say a 2x dilution or a 3x dilution. That's the same thing. A 2x dilution is the same as a twofold dilution. What it's simply telling you is the ratio between the old concentration to the new. In a 2x dilution, the old concentration was 2 times higher than the new. And so the new volume is 2 times higher than the old volume. In a 2x dilution, you just double the volume. So if I'm in the lab and I have a test tube and I know it has 5 milliliters in it, and somebody tells me I need to do a 2-fold dilution on that. All I have to think is, if I'm doing a 2-fold dilution, I need to double my volume. I'm starting with 5, so I need to dilute it to 10. That's how I do a 2-fold dilution. So if I dilute a 10 milliliter solution to 100 milliliters, how would you express that in words? 10 to 100. It's a 10-fold dilution or a 10x dilution. So that is our dilutions. Dilutions are simple. It's just this equation. You'll have 3, you'll solve for the 4th.
So you said the 10x dilution is the same as a 10-fold dilution?
Yes.
It's just a
Different way of saying it.
Okay.
So the last thing we talk about with solutions are what we call colligative properties. So a colligative property is a property of a solution that's going to change based on how much of a solute you dissolve, but it doesn't matter what that solute is. And so we're going to have equations, we're going to talk about these colligative properties, and we're going to talk about how many particles are in a solution. But we are not going to care at all what those particles are. We have 4 colligative properties. We have osmotic pressure, vapor pressure lowering, boiling point elevation, and freezing point depression. So our goal is to go through those 4. So for these colligative properties, we are going to make the assumption that if we have something that is soluble in water, it is a strong electrolyte. You remember, a strong electrolyte completely breaks apart. So if I have sodium chloride and I dissolve that in water, what does it break apart into?
Salt and chlorine.
Sodium and chloride ions. So if I dissolved sodium chloride in water, I would say that I get 2 particles from it. I get this particle and this particle. When I say particle, a particle can be an atom, it can be an ion, it can be a molecule, it can be a polyatomic ion, it doesn't matter. If they are bound together, if there's a bond holding them together, it is a particle. If I take potassium nitrate and I dissolve that in water, I get a potassium and a nitrate. That is 1 particle, that is another. I still get 2 particles. If I take calcium chloride, I get 1 calcium, but I get 2 chlorides. So this gives me 3 particles. So that's what we're talking about when we say it depends on the number of particles. It doesn't matter whether that particle is a calcium, a chloride, a nitrate, a potassium, a sodium, a sulfate, an acetate, it doesn't matter.
What if it was 2 CaCl2?
You'll never, in this type of a situation, you'll never have a coefficient.
Okay.
We won't be dealing with reactions where you would have a coefficient. So when we're dealing with something here, it's either going to be a strong electrolyte, meaning it's going to completely break apart, or it's going to be a non-electrolyte. It's going to be a molecular compound like sucrose. Sucrose is an example I'm going to use as a non-electrolyte on questions for this. If it's a molecular compound, it does not break apart, which means for every molecule that you start with, if I start with 1 molecule of methanol and I dissolve it in water, I get 1 molecule of methanol. This is liquid methanol, gives me aqueous methanol. It did not break apart. It is still 1 particle. Okay? This is also CH1030. So if I have a 1 molal solution of magnesium chloride, I need to find the concentration of the ions here. And now don't let the fact that it's molality trip you up. The math will be exactly the same as if it was molarity. You'll see why we're actually dealing with molality here later on. So it says I have a 1 molal solution. We need to find the concentration of the ions in that solution. In the end, all we need to do is we take the starting concentration, the 1 molal, and multiply it by however many particles it breaks into. So looking at our compound there, we have magnesium chloride. How many particles does magnesium chloride break up into when I dissolve it in water? 3. I get a magnesium and I get 2 chlorides. So there are 3 particles that come from that. I have 1 magnesium and 2 chlorides. So all I have to do is take my 1.00 molal solution, multiply it by 3. My starting concentration times 3 particles means I have a 3.00 molal solution of ions. A 1 molal solution of magnesium chloride is the same as a 3 molal solution of ions. Because there are 3 here. So it's 1 times 3 is 3. So now that we understand that, we can talk about the actual colligative properties. We're going to start with osmotic pressure. Osmotic pressure, in my mind, is the most difficult component. Okay? So osmotic pressure is based off of osmosis. Osmosis you've probably heard of before. Osmotic pressure, maybe not. So osmosis, the definition that people like to use is movement across a semi-permeable membrane. Okay? When we say a semi-permeable membrane, what that means is that the solvent can go through it, but the solute can't. In our situation, the solute's going to, the solvent, it will be water. So we're going to have a membrane that water can pass through, but whatever is dissolved in the water can't. So in this situation, we have a beaker of distilled water, then we have an upside down funnel with this membrane on the bottom, and we filled it with a salt solution. And then we're going to set the funnel in the beaker. When you have 2 solutions on either side of a semi-permeable membrane, the water is going to go towards the higher concentration of the solute. Water will always go towards the higher concentration. So in this case, when we started, there was 0 concentration in the beaker. It was just water. So when we put this in here, the water is going to go from the beaker into the funnel. It's going to go towards the salt. And when that happens, the volume of water in the funnel will go up, the volume of water in the beaker will go down. So what you need to get out of that is to remember, when you get two solutions on either side of a membrane, the water will go towards the higher concentration. If we had put pure water in the funnel and salt water in the beaker, the water would have gone from inside the funnel to the beaker. It will always follow the solute. Wherever the more solute is, the water will go. And so where the osmotic pressure comes from is for the water, in this case, to go from the beaker into the funnel, it had to go through the membrane. And the membrane is made up of a membrane that has holes in it. The water is trying to get to the other side of the membrane, but it can only go through where there are holes. So if water wants to get over here, it's trying to go from here to here, where the solute is, when it hits the membrane where there isn't a hole, it creates pressure. Just like our gases in our balloon hitting the balloon from the inside created pressure, this is going to create pressure when the water hits the membrane. So think of it as the more the water wants to get to the other side, the harder it's going to push on that membrane. So this is another way of looking at it. So in this case, instead of with a beaker with a funnel in it, we have a U-shaped tube. At the bottom of this tube is a membrane. So we can put different solutions on either side of the U, and they will meet each other at the bottom on either side of the membrane. And so if water wants to move from one side to the other, it can. In this case, we put water, pure water on this side, and we put a salt solution on the right side. The water is going to go towards the salt, and so the water over here moves over here. And when that happens, the level on this side goes down, the level on this side goes up. Another way of looking at this osmotic pressure, it means the exact same thing, it will give you the same number, is how much pressure, how much force do you have to push with on this side to make the water go back over here to make the two sides even. To me, the first way we thought about it is easier to comprehend. Just thinking about the water wanting to get to the other side, and it hits that membrane, the membrane is trying to block it, so the more it wants to get over, the harder it's going to push. To me, that makes more sense. It's easier to visualize than this. But they are both correct. Okay? I think of the other way as like people trying to get into Walmart on Black Friday. They line up at the door. When the door is still closed, they want to get in to get their $100 TV, and so they push so hard. When the door opens, everybody tries to go in through the door, and they end up breaking the glass around the door. Okay? Everybody wants to get in, so they're creating pressure on the membrane. So we can calculate osmotic pressure. Okay? This is probably one of the scarier looking equations we've had, but it's actually very simple. Okay? First of all, this is pi. Pi is a symbol we use for osmotic pressure. M is molarity. R is our gas constant from our PV equals nRT. It's still 0.0821. T is in temperature, and I is the number of particles that our solute breaks up into. So, pi is osmotic pressure, I is the number of particles that we make when we dissolve whatever we're dissolving, R is our gas constant, T is temperature, and M is molarity. So this is another term that people will occasionally use. We're not going to use it all too often, but if you ever see this, the IM together is called osmolarity. The M is molarity. The I, number of particles that we get, can also be called osmoles. A weird word, but you take osmoles, combine it with molarity, and you get osmolarity. To me, it's easier, rather than thinking of this as one thing, which can be confusing, just keep it two separate things. Keep the I and the M. The M is something you're familiar with now, and the I isn't that hard to comprehend. It's how many particles it breaks into. There's no good reason to combine them into this, but some people like to do that. So here's an example of our osmolarity problem. We are in the hospital, and we are going to give someone a glucose IV. We have to make sure that the osmolarity, the osmotic pressure of the solution that we're giving the patient is the same as the osmotic pressure in their blood. If it is not, there's going to be problems, and we're going to see what exactly that does. So we know the osmotic pressure of the blood is this, and our solution has to equal that. The question is, how much glucose should you dissolve in how much water? You have to make this solution. So we know our equation is pi equals m Im RT. Pi is our osmotic pressure. It's given to us. It has to be the same as blood. So pi equals 7.65. I is how many particles glucose breaks apart into when you dissolve it. Glucose is C6H12O6. Correct? Anybody else? Anybody taking anything that would? Okay. We're going to say that's correct. It doesn't matter. We're going to say C6H12O6. First of all, is it an ionic compound or molecular compound? Is there a metal in there? No. There's no metal, so it is a molecular compound. Molecular compounds do not break apart. So one glucose molecule gives us one particle. And so I is just one. Molarity is not up there. R is our gas constant, 0.0821. T is 37 degrees Celsius, which is body temperature. Okay? Because 0.0821 is our gas constant, our temperature is going to have to be in Kelvin. So we now have our temperature, our I and pi. All we're missing is m. If we solve for m, we get 7.65 divided by 1.0821. I get 0.3 So that is the concentration of glucose in molarity that my solution has to be? Unfortunately, that's not what the question is asking us. The question is asking us how much glucose should I dissolve in how much water? What I solved for is molarity. But we can use molarity to find how much glucose. Because molarity equals moles divided by liters. We know we have 0.3 equals moles. What volume of a solution do I need to have in the end? 1.5 liters. So if I solve for mole, I get 0.45 moles of glucose. So I need to dissolve 0.45 moles of glucose.
Into 1.5 liters?
Into 1.5 liters. Total. And so technically the correct answer would be insufficient water to make 1.5 liters of solution. It's not going to be 1.5 liters of water, because the glucose itself has some volume. And so you put the glucose in your beaker or your graduated cylinder, and then you add water and you stir it as you go until it fills up to 1.5, and then you stop. And you never actually know how much water you added.
Could you repeat the answer again? The way you said it.
So, dissolve 0.45 moles of glucose in sufficient water to make 1.5 liters of solution. Because if I say I made it, I can't turn around and tell you to add this much water, because I don't know how much water I added. So I'm basically telling you what I did. I added water until I got up to 1.5. However much that was. This is why it's important that when you give that patient their IV, that the osmotic pressure is the same as their blood. Because in the blood are the red blood cells. And inside every cell is a water solution. And so if the osmotic pressure on the inside and outside of the cell membrane are different, the water is going to try to cross that membrane to the other side, wherever the higher concentration is. So this is what a red blood cell normally looks like. Kind of looks like a donut, but that's not actually a hole, it's just a divot. And there's a divot on either side, okay? So if we put a red blood cell into a solution that is the same osmotic pressure as the inside of the cell, that is called an isotonic solution. An isotonic solution has the same osmotic pressure as the inside of the cell. If that's the case, water does not try to go anywhere, and so the cell stays exactly how it was. It will continue to look like that. If we put it into a solution where the inside of the cell is more concentrated than the outside, let's say we put it into pure water. There's no solute, there's no salt on the outside of the cell. And so the water on the outside is going to try to go inside where the salt is. It's going to go from low concentration to high concentration. And so the cell blows up like a balloon. If it blows up, it turns round. It can blow up until it's round, and then it can expand a little bit like a balloon, but it's not made to expand. And so if water keeps going in, it's going to blow up. That's called lysis. Say it again? Because there's no cell wall, which is part of the reason plants have a cell wall. It provides structure, and so that it can hold a whole bunch of water without blowing up. But animal cells don't have that. And so if too much water goes into that cell, it's going to explode. And I don't think I have to tell you that having your red blood cells explode is bad. The opposite of a hypotonic, hypo is low. Think of hypothermia. Hypo is low. The opposite is hypertonic. If you put a cell in a solution where the solution in the beaker is more concentrated than the inside of the cell, the water on the inside of the cell is going to go out. It's going to go towards the high concentration. And so your cells shrivel up. This is not as bad as that. Because you can imagine, you can recover from that. Once a cell blows up, there's no recovering. So if a cell shrinks, as long as it doesn't stay shrunk for too long, it can blow back up. If it stays shrunk for too long, the enzymes and things in the cell are not going to work, and that cell is going to die. So we have isotonic, where the concentration is the same inside as outside. Hypotonic, where the concentration outside is lower. In a hypertonic solution, where the concentration on the outside is higher. So that's osmotic pressure. Our second colligative property is vapor pressure lowering. For the most part, when we add a solute to a solvent, the vapor pressure of that solvent goes down. So we talked about vapor pressure a while ago. We said it's the pressure that a liquid likes to make as a gas above it in a closed container. So if this is water, we said that some of that water will evaporate to form a gas up here. So essentially what we're saying is when we add solute to our water, less of the water evaporates to go up here. Okay. So this is a party trick if you're at a very, very boring and unfortunately very, very, very long party and you want to impress somebody. Okay? You can take 2 glasses, one with pure water and one with a sugar solution, and bet them that you can transfer the water from one glass to the other without touching them at all. If you put a lid that covers the whole thing, the water is actually going to go from the pure water glass over to the sugar glass. And if you wait long enough, it will completely go over. It's going to take you weeks though. But if you made a bet, you might as well win. So it's because pure water has a higher vapor pressure. There's more of this water becoming gas than the water in this one. Because this one has a solute, it holds that water here. So it's evaporating here faster than it's evaporating here. So if it's evaporating faster here, when it's up here, it wants to go where the sugar is. Just kind of like the osmotic pressure. Once it's up here, it's going to go towards the sugar. And so in the end, what happens is the water comes up in the gas, back over here. So the way I think of it, and I'm going to draw it, and you're going to laugh. If I have a beaker, and there's water in that beaker, for the water to become a gas, it needs to escape up out of here. The way I picture this in my mind is if I dissolve something in that water, some of those particles, say some of my sugar, are up here at the surface of the water, acting sort of like a goalie, preventing the water from escaping. And so, some of these water molecules, when they go to try to escape, they hit a solvent molecule and bounce back down in. So that makes the water evaporate more slowly. This is very, very, very similar to our next colligative property, which is boiling point elevation. So this is vapor pressure. We deal with vapor pressure when our liquid is below its boiling point. So vapor pressure is a slow process. That's you sitting a glass of water on the table and letting it evaporate. The third colligative property deals with boiling point elevation. So in boiling point elevation, when we add a solute, it changes the boiling point of that solvent. When we dissolve something in water, it changes the boiling point of the water. And it does that because it changes the vapor pressure. So they are two very closely related ideas. You can kind of think of them as essentially the same idea. In boiling point elevation, you still have these solute molecules acting as goalies. And so, in order to get the water to boil, to overcome the goalies, you're going to have to heat it to a higher temperature. Boiling point elevation, raising the boiling point. How many people ever put salt when they make in the water when they make spaghetti? Did you ever know why you were doing it?
To keep the spaghetti from sticking.
Really? I don't think it does that.
To keep the spaghetti from sticking to the pot. Yeah. Oh,
Well,
I don't know if it does or not.
I don't think CHM makes it stops it from
No?
sticking. A lot of people think they're doing it for taste. Now think about it. When you do this, how much salt do you put in there? Just a sprinkle. If you put a sprinkle of salt into that much water, think about how much of that water ends up in your spaghetti. And then you cover the spaghetti in salty tomato sauce. That little bit of salt you put in there is not going to change the taste. And so what it does is it changes the boiling point. And a lot of people are going to say it makes the water boil faster. And it doesn't even do that. It makes it boil at a higher temperature, which means it has to get to a higher temperature before it boils, so it's actually going to take longer to get there. So, there is a benefit of doing this. We've debunked all three of...
I haven't debunked one.
I think I debunked it by just saying that doesn't make sense, and I don't think it's right. It cooks the pasta faster. Yes. We're boiling at a higher temperature, and so it cooks the pasta faster. It takes longer to get to that temperature, but then once you're at that temperature, the pasta cooks faster. And so, you'd have to do an experiment to figure out, do you lose more time because it takes longer to boil than you gain with the pasta? I don't know the answer to that. But if you work in a restaurant, say Olive Garden with never-ending pasta bowl, and you're never-ending putting pasta into your water, you want to get it churned around as fast as possible. So in that case, you have your water boiling constantly. You get it to that temperature, you just keep it there. Then you put pasta in and take it out. Put new pasta in and take it out. Because it's boiling at a higher temperature, you can leave that pasta in for a shorter amount of time. Our last colligative property is freezing point depression. So where we took boiling point and elevated it, we're going to take the freezing point and lower it. Essentially what we're doing is when you dissolve something in your water, you are making it want to stay a liquid. You're going to have to heat it higher to make it boil, and you're going to have to make it cooler than normal to make it freeze. It wants to stay a liquid. How many people have lived up north? What happens when it snows? They put salt on the road. Now the question is, why? What is that going to do?
It melts the ice.
It melts the ice, but why? Based on science. It lowers the freezing point. So normally, water would freeze at 32 degrees Fahrenheit, right? But if you put salt on the road, and that salt dissolves in the water, all of a sudden, that water now freezes at a lower temperature. Say we now lower the freezing point of the water to 25 degrees Fahrenheit. And so where you would have had ice on the road at 30 degrees, you now just have water. If you've lived up north, what happens when it gets really, really, really cold and it snows? You remember? They they stop putting salt on the road. Well, you got plows. Not up north, no. Unfortunately, you never get to not go outside. They cancel school, but they don't cancel work. So I said, when the salt dissolves in the water, it lowers the freezing point. But what if it's so cold that there is no liquid water for the salt to dissolve in? It's all ice. You put salt on ice, it's not going to dissolve, and it will never lower the freezing point. And so, if it is so cold that you have only ice and no liquid water, the salt won't dissolve. So stop putting salt and you put sand. Sand just creates traction. The sand doesn't change the freezing point at all. It just gives you extra traction on the ice. Another way we can use this to our advantage is in a cooler. Has anybody ever added salt to a cooler of ice? Never. Mythbusters actually did this one. So think about it. What would be the advantage of adding salt to our cooler of ice? If I have a cooler of ice with no salt, what temperature is my ice? 32 degrees Fahrenheit. It's the freezing point. When I add salt, what's going to be the temperature of the ice water in my cooler? It's going to lower. And so now my cooler is colder than 32 degrees Fahrenheit. And so, one, if you take a warm drink and put it in there, it's going to cool off faster. But also, once it cools down, it's going to be colder than if you put it in regular ice. So if you put a Coke into just regular ice and let it sit there, it's going to be 32 degrees.
Does it keep the ice frozen longer?
No, it's actually going to make it melt faster because of this.
Okay.
You're doing the same thing.
Okay.
But having the ice itself doesn't really matter. What matters is the temperature. And so we convert some of our ice into water, and it ends up lowering our temperature.
So is that why, like, when we make homemade ice cream, we use the...
Yes, that is exact. How many people have made homemade ice cream? Did you do it in a fancy churner, or did you do it in the Ziploc bag method? Ziploc bag? You had the actual maker thing. So they both work the same. So for you, there was a big bucket that you put ice and salt, and then inside of that was a bucket that you put your ice cream in, right? And for the Ziploc bag method, you put your ice cream ingredients in one Ziploc bag, then you put that bag inside of another bag that was slightly bigger that contained ice and salt. And so because you have the ice and salt around your ice cream, it allows you to get it really cold. So you want your ice cream to freeze, right? Otherwise it's just sugar milk. And nobody wants that. And so, milk is mostly water. It is water with things dissolved in it, which means we have freezing point depression in our ice cream. To get it to solidify, we have to get it below the normal 32 degrees. And so the ice we're going to use to freeze it has to be colder than 32 degrees. And so we have to put the salt in the ice to get it cold on the outside so that we can freeze the ice cream on the inside. Okay. So those are our 4 colligative properties. The types of questions that you're going to see for these are, rather than making you calculate freezing points, because there are equations for that, and there are equations for calculating boiling points and vapor pressures. What I want you to know is be able to figure out the trends. Which way is it going to go? And also, which solution will give you, let's say, the highest boiling point? So this is an example. We have 3 solutions. 0.2 molar salt solution and a 0.5 molar sucrose solution and a 0.3 molar sucrose solution. Question is, which solution would have the highest boiling point? So think of it. The boiling point, what is the colligative property for boiling point? Is boiling point elevation. And so the one that ends the highest is going to be the one that went up the most. And the one that goes up the most is going to be the one that has the most particles in it. So we have our 3 solutions. We have our 3 solutions. We have to figure out which one has the most particles in it. So our first one is 0.2 molar NaCl. How many particles do we get from NaCl? 2. So I'm going to take that concentration times 2 equals 0.4 molar particles. Our next solution is 0.5 molar sucrose. Sucrose is a molecular compound. It does not break apart. So times 1 is 0.5. And our last one is 0.3 molar sucrose. This one is 0.3. So this one, I know 0.5 is larger than 0.4. This one has the most particles. So this one is going to have the highest boiling point. Because it has the most particles, it's going to change the most, and so it's going to end the highest. So which one will have the lowest freezing point? Say it again?
Wouldn't that also be the one?
Yes. So it's boiling point elevation. The one with the highest boiling point changes the most, and it's freezing point depression. And so the one that changes the most will have the lowest freezing point. So again, it's this one. The trick is to remember to multiply the concentration by the number of particles. If this was a 0.3, you would have gotten 0.6. And so even up here, even though up here it would have been 0.3 versus 0.5, this one would actually have had more particles. So don't forget to multiply the concentration by the number of particles. We're out of time. Take a look at this. It's basically the same as what we just did here. It's just written out in words instead of pictures. You will see questions like this, though,